Welcome to Hidden Layers, where we explore the people and the technology behind artificial intelligence. I'm your host, Ron Green. I'm excited to have two AI industry veterans, Paco Nathan and Dr. Steve Kramer, joining me today. Together, we're going to discuss graph neural networks, an increasingly important technique within AI for modeling complex relationships and everything from molecular structures, recommendation systems, weather forecasting, and much, much more. Paco Nathan is managing partner at Derwent Incorporated and author of Latent Space, along with other books, popular videos, and tutorials about machine learning, natural language, graph technologies, and related topics. He's known as a player coach with 40 plus years of tech industry experience, ranging from Bell Labs to early stage startups. Paco holds a BS in mathematical science and an MS in computer science, both from Stanford University. Dr. Steve Kramer is chief scientist at Kung Fu AI and has over 3 decades of experience in artificial intelligence, data science, and software management. He earned a PhD in physics at the Center for Nonlinear Dynamics at the University of Texas at Austin. His research covers a wide range of fields, including machine learning, anomaly detection, deep learning, and predictive analytics. Paco, Steve, thanks for joining me today.
Absolutely.
Okay, before we jump into any detail, Paco, maybe let me ask you, set the table for us around graph neural networks. What are they at a high level?
Great. Well, I mean, we see in real world data, all kinds of examples, different verticals. Data is typically linked together. There's different kinds of connectedness. And so graphs are a really good way to understand that. And the idea was, you could do graph databases, do queries, and understand what's inside your graph database. But graph ML is a general area. Graph neural networks is within that of how can we apply machine learning to the connected data that we have and be able to come up with other data products or inference or some sort of AI techniques to really leverage that. And GNNs, graph neural networks in particular, they just really took off, I guess I would say probably late 2010s, going into about 2021, 2022 kind of, you still see it, but there was this huge growth and then it ramped. Right. And so for a while, if people were getting their dissertation done, they wanted to get published in a conference like NeurIPS, a really popular machine learning conference, you had to have those letters GNN in it.
Right.
But it kind of begs the question in industry, it's like, well, if there was so much emphasis, where are all the applications? And I think that this is something really interesting now because we've seen such a boost in interest and usage in AI. LLMs are definitely all the headlines. Now we're starting to see production use cases trickle in, or rather start to become disclosed, where, yes, in fact, we're using graph neural networks to augment what we're doing with LLMs.
Right. For some examples there, I was looking in preparation for our conversation today, DeepMind recently released and open sourced a graph neural network model called GraphCast. And this is really interesting because it's the new state of the art for 10-day weather forecasts. And because of the graph nature of the model, they say that they can generate 10-day forecasts literally in seconds compared to hours before. So is my understanding, and I've never worked with graph neural networks directly myself, my understanding is because you can break the relationships down directly through sort of graph structure, it can dramatically reduce the amount of computation required for certain problems. Is that correct?
I mean, yeah, that's a good characterization. One of the problems in graph technologies in general is that if you've got connected data and you need to go from point A to point B, but through several different waypoints, like you're at a location, you're trying to drive somewhere else,
right? And
you're on Google Maps. It's like, how do you find that route?
Right.
Same thing with your enterprise data if you're trying to navigate a supply network. And the thing is that if you try to do that in SQL, you run into something that we call the self-join problem. SQL indexing thinks that one table is going to be indexed with another table. SQL engines do not think that one table is going to be recursively indexed with itself thousands of times. That just brings it to its knees, typically for most SQL engines. So, by leveraging the graph, you can really cut down a lot of this computational effort by working with graph algorithms directly.
Okay, that's great. Steve, retrieval augmented generation, a technique within NLP these days is really popular. We've talked a little bit about using sort of knowledge graphs, which are, pretty closely related. Can you talk a little bit about that and where you're seeing it being used in some of the projects you're working on?
Yeah, so there's been a lot of interest in that because knowledge graphs basically are grounded. They have sort of known, verified entities and relationships that have been vetted. And as we've seen before, even though there's so much interest in LLMs, they do hallucinate because they're fundamentally, probabilistic in nature.
Right.
And so what we're seeing in many cases, even though people are excited about things like ChatGPT, they realize that, well, they are just not by any means ready for prime time in and of by themselves. So there's, standard RAG, which is, I think, more based on like vector embeddings, vector databases, and then graph RAG, which I know, Paco, you've started to do a lot of work now, is actually sort of marrying knowledge graphs with LLMs. And so I think, and a lot of folks have found even better results with smaller models. You don't necessarily need large language models. You could have a sort of a smaller, medium-sized language model. If you marry that with a knowledge graph, you can get much better results without the hallucinations.
Let's talk about that area a lot, because this is obviously pretty hot right now. Language models, probably the hottest thing in AI right now. The biggest problem with them is hallucination. So anything that can help curb that. Can you share some of your experiences leveraging graph systems to kind of tamper that down?
Yeah, I mean, the idea with LLMs is you've gone and you've taken all this input, trillions of tokens, right? And so there's almost kind of like a general sense reasoning aspect to them of where they've just seen so many examples of language, of syntax, and they can draw on that to come up with something that's a pretty reasonable answer, And okay, maybe, I was looking at a use case recently where there's like 2% false positives on something, and people are like, oh, that's nothing. I was like, if you're actually like a large metro police department and you're deploying a SWAT team, 2% false positive is really, really bad.
It's unacceptable.
Right?
I would even argue, even if you're dealing with text, I mean, if 2 out of 100 words were wrong, I mean, that's problematic.
It's going to hit you, yeah. So this is the idea is that we could train larger and larger models that have more and more general stuff in them, but how do we really tie them down to the things that are important for you in your business case? Right. And you can make the argument of, well, just go and train more for you in your business case, but that's also additional cost. Right. So by having this more like a hybrid approach, you can ground what's going on internally inside the large models without having to spend so much more to do this purpose-built model. You can use something that's like an open source model, cheaper to use, less expensive to do inference, at the edge and all. But then you also have the ability to go in and change and update, curate, iterate on your knowledge graph so you can get new stuff in there really quick. When you look at like ChatGPT, there's a latency. It was trained at a particular point, a snapshot of data. And okay, they're doing updates, but there's still latency.
Yeah.
If you've got your own graph or your own domain, you can get in there and change stuff right now.
Right. And you're talking about latency not in the generation, but in its knowledge, the knowledge it was trained on. Yeah,
like for instance, if you're providing some sort of service and you get hit with, okay, here's a data privacy compliance issue, you have to redact this. What's the latency between getting that notice and making sure that stuff in production is compliant with the notice?
Yeah, that's a great example. That's a really interesting example. I've never even thought about that before, because it's one thing to add to a model. It's a lot more difficult to take something out of a model.
Exactly.
Okay, that makes a ton of sense. Okay, so how do you represent graph information within a vector?
Yeah, that's the big problem. And so the thing is that with graphs, we say graphs really bring to surface relationships. When we talk about like SQL data warehouses, analytics in general have been very much reliant on things like fact tables. It's all about, I've got some schema, the relationships are fairly static, but then I've got a whole bunch of facts that I can surface, and I can show you week over week numbers on your sales facts. But what are the relationships going on between there? And when you find interesting ones, can you layer on new stuff without changing your whole database schema? That's where graphs become much more powerful. The trouble, though, is now we have a problem because graphs are this kind of geometric shape. And the patterns that you see in graphs repeated, like if you're looking at your, in manufacturing, like bill of materials, there are going to be graph patterns that show up for your customers over and over. Those are shapes, and shapes don't necessarily fit into vectors. There's a general class of algebraic objects. We could talk about tensors and whatnot, but long story short, you need a vector. It's hard to get a graph into a vector. What you can do, though, is take a look at a neighborhood in a graph and search around it and say, okay, what are my nearest neighbors? What are their attributes? What are the relationships going on? So you can kind of get a snapshot and think about moving the lens across the graph in different places and just sampling.
Okay, let me dig in there to make sure I understand. When you're sampling around, are you taking a node within that graph network and then sampling around that?
You could think of that, or maybe a couple of nodes, or some subset of nodes,
or a broader section. Okay.
And so why are you sampling it? You want to build a vector to represent and do representation learning, but with a graph. And so is that so you can predict nodes? And so that's one kind of embedding. Is it because you want to understand the relationships that are connecting things? That's a different kind of embedding. Or are you just trying to get a subgraph, like a snapshot of the graph? That's a graph embedding. So there's like three kinds of strategies to go from graph data to vectors. And the type of GNNs usually kind of trade off on that. Some do some hybrid approaches.
Is there anything dominating out there?
Wow. Like I said, you look at the graph of the interest, and it just ramps up in late 2019. It's crazy. So there's so many different variants that were tried, and geometric learning and hyperbolic learning and on and on and on. What they found is, wow, it's a lot of work. And now it turns out that the industry teams are starting to surface use cases where they've been a bit more pragmatic, a little bit less academic. They've come up with trade-offs that actually work for the use case.
Right.
So I think what we're going to see is I think we'll see a lot of this is really tuned more toward the use case. There's a real fundamental problem, not to get too mathy, but when we talk about graph theory, we roll back to Budapest a century or two ago, there is a notion of graph theory, and it's great mathematically to describe nodes and edges. It's a bit lacking when it comes to what we do in practice in industry with graphs. Graph theory doesn't cover the labels and the different attributes, properties and whatnot. It doesn't cover the probabilities. And so a lot of people in research, they start out, stating the famous equation, G equals, VE, and it just isn't good enough to handle the industry use cases. So I think that we will see more research that's maybe coming off of industry that's a bit richer, but more tuned toward the use cases.
Okay. Steve, are there any example uses within graph neural networks or graph knowledge networks that you're particularly excited about right now?
Well, another area that I've been passionate about for a long time is actually time evolving graphs. So you can think about social networks that evolve over time. You can think about there are cybersecurity applications if you look at the interconnections among nodes within a computer network. So that's very important for things like cyber defense against attacks. And so I think it's just really fascinating to see that you can use all these different GNN-based approaches, because it's fundamentally there's not labeled ground truth examples, and so everything is changing, everything is evolving, but you want to find some way of surfacing these anomalies that could be risky, but not overwhelm the operators with tons and tons of false alarms. So that's kind of always one of the challenges that you face in a lot of these areas.
Well, we've got another presidential election coming up, and you did a lot of work. I remember last election around sort of bots within different social media platforms, and I know you were leveraging some graph tools and techniques there. Maybe just share a little bit about that work.
Sure, absolutely. So there, it's kind of cool that work didn't even require full GNN, graph neural networks, not necessarily deep learning based, but just looking at, patterns of information entropy, looking at randomness. So sometimes you could look at just the spacings of timing between posts was one way of characterizing it, and also looking at the sort of the complexity, the ordering of the tokens within posts. So and the fundamental insight there was that humans ideally are more complex than simple simple programs. And so it used to be that when I started doing that particular work back in 2017, bots were much simpler. Well,
Right.
of course, as we've seen with all these new generative models, they're just lots more complex behaviors. So they're getting closer, but you can still detect them. And I think the example that came 2 years ago with the invasion of Ukraine, I found, I identified over 6,000 highly automated accounts. And that's even though the technology on that adversarial side has advanced, but you can still find them. So
Right.
it is definitely a big concern. And I know that a lot of folks are very concerned about election integrity with the elections coming up.
I want to cover some more example of real-world production uses of graph neural networks. I know it's being used actively in areas of sort of fraud detection. Can you talk about that a little bit, Paco?
Yeah, definitely. I mean, just kind of building on what you were talking about, Steve, one area where graphs get used a whole lot, and actually looking at the large open source projects in this area, inevitably you see the finance use cases driving a lot of activity. A lot of that has been because of something called KYC, know your client. So internationally, if there's money being transferred, if you're extending credit, you have to, as a financial institution, you have to be able to say, we've done our due diligence. We think that these people are legit. We are not laundering money for a Russian oligarch or a terrorist organization or whatever. And that's graph work, right? I mean, you look at something like the Panama Papers. That was graph analysis to actually go and do the investigation.
Right.
And so we see finance really driving this a lot because of fraud. But also, you go out into other places. Definitely pharma has had so many use cases, life sciences in general. But
let's talk about that, because that's a great area. So we did a podcast a few months ago with a wonderful PhD candidate working on protein folding using AlphaFold 2. And one of the key technologies within AlphaFold is the graph neural network representation, where they're using it to model aspects of the different atoms and the relationships between them. Let's talk about some example use cases within pharma and healthcare broadly.
Yeah, it's great. I mean, so much on I've heard from friends. I'm not an expert in this area, but I've heard from friends that what happened with protein folding, it'll be decades before we figure out exactly the magnitude of how important that is.
I agree.
And then you go past that into other related areas, even getting into material science, understanding molecular discovery. So there's a lot in terms of pharma with drug discovery. There's a lot in the manufacturing space with going into material science. These are all kind of tangential. And, a lot of that has come out of machine learning work in say, cancer genomics, where inherently there are effects between genes. There are effects that go out into expressions of diseases. These are all graphs.
Right.
And so just building up on that. But, you get into other areas too, even like sales, like trying to do prospecting is really good area for graphs.
Yeah. Well, I remember, a few years ago, it seemed like graph neural networks kind of exploded on the scene out of the blue, and there was a little bit of a sense that I think that they were going to have a wider adoption than they did. I think we all three kind of agree that it was large language models that maybe kind of sucked all the oxygen out of the room. What's your thought on the future with graph neural networks? Do you think that the important work that's being done with them right now is not getting the attention it should be?
I mean, I think that there's a kind of latency. I think in AI, I'm going to reference something from Luke Biowald out of Weights and Biases, did a talk years ago showing where, here's a famous algorithm. Here's how many years before we found a data set to show a really killer use case for it.
Right.
So there's a period of years between some kind of algorithm being published and some sort of data validating it. But then going in industry, there's also a period of years of staffing people who know how to use this expertise.
Right.
And then a period of some time before you can get the POCs out and actually validate that you've got a use case and then push it into production.
Right.
And then there's a third kind of latency too, because a lot of companies don't want to talk about this stuff. And often it seems to be the case, I'm not throwing any shade, but it seems to be the case that once the HR departments figure out that they're going to lose some of their top talent, people are able to publish a lot more freely.
Yeah, and then all of a sudden they're a little bit more open. Yeah, exactly.
Yeah. Just, I don't know, there's some kind of relationship. So that you get this multi-year inherent latency. And so case in point with graph neural networks, friends over at Neo4j, they did a big study, I think it was really only like a year or year plus ago, and they were trying to dig in. They're like, hey, this seems legit. Maybe we should really focus on these kind of use cases. What is out there in production, graph neural networks? And so in early 2023, I believe, they came back with not a whole lot. I mean, nobody is saying that we have anything in production. Even in places like Meta that had really been talking it up before, they're like, we pulled back. But then a year later, we see something from Spotify where they had a project and now they're finally publishing it. But one of the great use cases is in audiobook recommendations because you have really imbalanced data. It's like a small, tiny fraction of people on Spotify or wherever, they're the ones who listen to audiobooks. How can you generalize out to a whole broader population that doesn't? You don't have any data to represent it.
Right.
And so what they found at Spotify was by using a hybrid, they call it a two-tier model or two towers model on the LLM side. And then they have a graph and they use a GNN. They can actually get enough traction out of the data to do commercially viable recommendations.
And it's basically the cold start problem within recommendation engines.
Yeah,
more or less.
In some really counterintuitive ways. If you read what they've published, one of the things they said was, the typical RecSys, like collaborative filter approaches, the matrix factorization that you use there, just bombed. Couldn't use it.
Interesting.
What they did was they did a graph, but they made sure that the nodes in the graph are not users. They're more like concepts or trends about users. And so they had to juggle a bit, but they came out with some interesting representation, very counterintuitive, but it's led to really nice revenue stream, building a business in an area that you really couldn't be doing much with machine learning before.
Right. And I've seen, I know Pinterest in particular does a lot of work on their recommendation engine around modeling the pins, the actual things that people are saving and a way to model them in sort of this much more complex, rich space than they had before.
Oh, absolutely. I mean, they're exemplars there because also Yuri Leskavec, very much involved with Pinterest, but also leads the lab at Stanford that a lot of the graph embeddings, a lot of the graph neural network stuff came out of.
Right.
So the SNAP project at Stanford, I think that if people want good resources, particularly there's William Hamilton came out of that. And he was one of the people that came up with GraphSage. And that lab has spun out a lot of stuff.
That's a great area. What should people do if they're interested in graph neural networks? Are there any specific papers or areas or projects that you would recommend they take a look at?
I mean, the cool thing, and Paco and I were just talking about this at lunch earlier, there's like, the cool thing about graphs is there's so many different ways you can start exploring them if you have kind of simpler end user interfaces or, friendly tools like Neo4j. Obviously, if you want to go hardcore into understanding the deep mathematical underpinnings and overlaps with differential geometry, Michael Bronstein is an amazing researcher. And the other thing that I really enjoy about graph learning is it's so interdisciplinary. You have people from computer science, math, physics, computational biology, computational sociology. So basically, literally any field you can jump in and find some angle of graph learning that you can use. So what we'll do, I recommend we'll curate a list of resources because
okay, great.
We'll make sure to put great lists of resources for graph learning.
Okay, fantastic. We talked a little bit earlier about how graph neural networks can be used to augment large language model, retrieval, augmented generation type systems to reduce hallucinations. What other ways are you seeing it being leveraged there? Because that's just one of the hottest areas.
Yeah, no, I mean, RAG is really super interesting, super useful. It is still feels like it's a Band-Aid. Yeah. It's something after the fact.
I totally agree.
But when you look at it, how it's kind of deconstructing the whole process of how we're using LLMs, there are places where graphs really fit in. So one of the things that's happening right now is a lot more discussion about hybrid AI approaches. You'll see this under the umbrella of neurosymbolic is usually what people call it. But the idea is that the people over on the more symbolic side of inference have been doing their thing, and the people on the more statistical side have been doing their thing. They don't present in the same conferences. They don't know each other.
No, not at all.
And now we're starting to see places where these start to fit together, and oh my, it's really good. You get benefits out of both. RAG is one of the early areas, but if we take and look a little further out, where is RAG going and where are LLMs going? And we know that these things are both going to evolve. There's a lot more room ahead for incorporating the symbolic parts because it actually fits what's going on in the brain. Like if I'm out trying to hit a ball with a bat, right?
Yeah.
I've got a lot of motor coordination going on. If you were to use just the sensory input kind of modeling that we see represented in deep learning, you would never be able to swing that bat fast enough. You have to have games being played in a body with cerebellum where fast signals are being propagated that are more conceptual, that are not just purely sensory. And so that's how animal brains are able to deal with the real world.
Mm-hmm.
It's not something that the deep learning side, the statistical side has really accounted for. We're starting to see snippets of it, like semantic loss functions being worked into newer kinds of deep learning models where you actually use the symbolic side to help on the training of the statistical side.
Okay.
So I see rolling out, you'll see a lot more of these kind of hybrid architectures.
Okay, that's really fascinating because, the divide between the symbolic AI and, neural AI world is so huge right now. Paco, that might be something I have you back on again soon. Maybe we'll dig into that a little bit. That sounds fascinating.
Looking forward.
Well, I appreciate both of you taking the time. This couldn't have been more fun. Thank you so much.
Thank you. This is great. Thanks, Ron. Yeah. Thanks, Paco.
Thank you for listening to Hidden Layers. This series is hosted by Kung Fu AI, a management consulting and engineering firm focused exclusively on artificial intelligence. If you have any questions or thoughts about today's episode, or if you know someone we should feature, please visit us at kungfu.ai.